All right, so for problem number 7, they're asking us to state all of the x and y intercepts of this function f of x, and then to sketch the results. So this is one of those problems where we have to deal with things like multiplicity, and we need to deal with end behavior, and really take into account all of the pieces that are going to go into giving us this sketch. So what we did with most of these during the year is we actually, before we ever got started with doing a sketch, is we made a list. So we said, in this case, this is a degree. Okay, let's figure out what the degree is. Okay, a degree, it looks like I have a factor x minus 2. I have 3x plus 1s, so now we're up to 4. And don't forget that I also have this negative 3x at the beginning. That's going to contribute a factor as well. So I actually have, in this case, 5 factors, counting all of the duplicates, which makes this a degree 5 polynomial. I just added up all of the pieces that made the original expression. Right? So in this case, is a degree 5 polynomial. If we talk about the end behavior of this expression, okay, we're going to say a degree 5 is odd. Okay, so odd means it travels in different directions. And because my lead coefficient is a negative 3, okay, I know that this is going to be up on the left-hand side and down on the right-hand side. Okay, and so if you want to remember, we had this thing called limit notation. And instead of writing up and down, what we can do is we can say as x approaches negative infinity, and what this means is I'm describing the left-hand tail. Okay, I'm going to say f of x approaches, well, it's going up, so it's going towards positive infinity, right? And then when I describe the right-hand side, the right tail of the graph, I'm going to say as x approaches positive infinity, which is, again, just a math way of describing the right-hand side of the graph. I'm describing the end behavior on the right-hand side. Since it's going down, I'm going to say f approaches, okay, negative infinity, okay? Or f of x, right? So this is another way of writing up, down, right? For our sketch and for this particular problem, we don't need to worry about limit notation, but it's something that you may have to worry about, so I'm just reminding you, right? So we haven't answered any of their questions yet, so let's start getting into those little details, okay? In this case, they're saying state all of the x and y intercepts, so let's state the x intercepts first. The x intercepts are, when I set each of the factors equal to 0, what do I get? Okay, so I'm going to say x intercepts. Let's give it a nice little heading here. Okay, so my x intercepts are when I set 3x equal to 0, or negative 3x equal to 0, right? Negative 3x equals 0, right? I'm going to say when does x minus 2 equal 0, and when does x plus 1 equal 0. So whatever your expressions are in factored form, set them equal to 0 and solve. So in this case, I get an x-intercept of 0. In the second one, I get an x-intercept of 2. And in the third one, I get an x-intercept of negative 1. Those are the 3 zeros, or the 3 x-intercepts in this case, that I'm going to get, that I'm going to graph. So let's put those on the graph before we forget about them. Okay, so I have 3 zeros. I have one at the origin. Okay, that's x equals 0. I have one at 2. Okay, and I have one at negative 1. Okay, and remember what we did when we did problems like this. We actually, when we were drawing the end behavior, we kind of sketched the arrows so we knew in what direction we were going. So in this case, because it's down on the right, I know coming out of the very right-hand x-intercept, it's going to be traveling down, okay, and coming out of the very left-hand one, it's going to be going up. Okay, we don't know how it's going to bounce off that point yet, or if it's going to go through the point. We're going to discuss that in a moment. Okay, so to find the y-intercept, okay, the y-intercept is going to be plug in a 0 and tell me what comes out. Right, so if I plug a 0 in for x, here's what my expression looks like: negative 3 times 0 times x, or 0 minus 2 times 0 plus 1 cubed. Okay, so if I simplify this, guess what you get? A big 0. I'm multiplying a 0 by, it doesn't matter what these other things come out to be. When I plug in a 0, I got back a 0. So the y-intercept is the point 0, 0. Guess what? We already graphed that. That's the origin, right? We graphed that when we graphed x equals 0. Right? So we've actually already got that point down. So we calculated it. We showed the calculation because they asked us to state the y-intercept, right? And we have everything we need. So the only thing that we have left to take into account is, okay, when I'm talking about the x-intercepts, I need to describe one of them in a little bit more detail, and it's this x equals negative 1. If you notice, x equals negative 1 came from x plus 1, which was cubed, and because it was cubed, there were actually 3 different x plus 1s that all gave us the same answer. So I'm actually going to say right below this that there was a multiplicity of 3. And that's telling people, hey, by the way, there wasn't just one x equals negative 1, there's actually 3 of them. But since we're graphing the same point over and over again, we're not going to see that show up on the graph. Okay? So when I graph this, here's what it's going to look like. When I go through -1, I need to make sure this acts like a cubic function, which, if you remember, for cubic function, the parent function kind of looks like turn and turn again. So when we go through through this point, x equals -1, we need to make sure that happens. So I'm going to just, as best I can, sketch this. It's a little tough, right? It's turn and turn again, okay? And then it's going to have to turn around to go back through 0, right? X equals 0. There was no multiplicity at 0, so it's going to shoot straight through. So I'm going to do a pretty sharp turn to get this to go around, okay? And then I need to turn one more time to hit x equals 2. Again, it's going to go straight through there because there's no multiplicity, right? And it's going to look something like that, and that would be a pretty good representation, right? We state all of the x and the y intercepts, 3 x-intercepts and a y-intercept, right? And then we graphed a sketch of what f of x looks like. Okay, so let's talk about average rate of change. So f of x in problem number 7, right? That's this one right here. So we're going to say -3x. See if I can remember this. -3x, x minus 2, and x plus 1 cubed. Okay, that was f of x. Right. So we're going to use this function, and now what they're asking us to describe is the average rate of change from over the interval from -3 to 0. So if you take a look at our graph real quick, what we're really describing is kind of from -3 to 0, this little piece of the graph. What's happening? Is it diving sharply? Is it rising? Is it turning? We're trying to give a number value that describes what's happening on that little section of the graph. So to do that, if you remember, we kind of used something that was similar to the slope function, where what we did on the bottom was we had the two x values at the ends of the interval, and we subtracted those. So we said -3 minus 0. Okay? And then on the top of the function, we had what happened when we plugged those points in, right? So if I take -3 and I evaluate this function at -3, we'll do this off to the right-hand side in this gigantic space that I've left. I'm actually going to do f of -3, and we're going to find out what happens. So let's get, in this case, it looks like -3 times -3, okay, times -3. Let me get rid of that. Okay, -3 times -3, okay, times -3 minus 2, okay, times -3 plus 1 cubed. Okay, so let's simplify this in pieces. -3 times -3 is 9. Okay, -3 minus 2 is -5. -3 plus 1 is -2. And -2 cubed is -8. Okay, so I just simplified each of the terms separately. Okay, and now my job is just to multiply these together. Well, -5 times -8 looks like 40, positive 40, right? And 40 times 9 is 360. Okay, so I'm going to say when I plug in a -3, I got back a 360. I'm going to put that answer right above -3. Okay. The other one's actually pretty easy. When I plug a 0, we've already done this when we found the y-intercept. When I plugged in a 0, I got back a 0. Right? So in this case, I'm going to say 360 minus 0, well, that's 360. Okay? 360 or -3 minus 0 is -3. So this is 360 divided by -3, and that in this case is -120. Okay? So our average rate of change over the interval from -3 to 0 is about -120. So it's actually diving very sharply down, which is something that we would expect in a cubic function. That's the way they usually look. Okay. Problem number 9. Write this expression as the product of linear factors. So again, don't be thrown off by the language. The product of linear factors just means factor it. Right? Factor completely is the language that we usually use, but it means the same thing. Right? So if I see anything like this, remember, higher order polynomials like x to the fifths are probably going to have some kind of GCF in them, and in this case it looks like they have an x squared. So let's remove the GCF first. Okay, and it looks like I have x squared, and then I have x cubed plus 5x squared minus 9x minus 45. Okay, and now that GCF's out, I'm going to look at each of the terms and say, can I factor each of these terms again? In this case, x squared's done. That's just a GCF. But this remaining expression here, I can do more with that. And I can use the grouping method and say, let's remove an x squared. Okay, and it looks like I'm left with x plus 5. Okay, and then it looks like I have a 9 or -9 in common in my second group. So I'm going to say, remove the -9. And I have another x plus 5. Those matching x plus 5s are my confirmation that this does actually factor. Right? Sometimes it doesn't work out, but in this case it did. So I'm going to say x squared minus 9 and x plus 5. And then we're not going to forget that around this entire big expression, that x squared was sitting out front the whole time. So I'm going to bring that down and not forget about it. Okay. However, we are still not done. X squared minus 9, if they're saying the product of linear factors, linear means highest exponent of 1, and that means that x squared minus 9 has to be broken down one more time. So in this case, this is x squared minus 3 squared, so I'm going to turn that into x squared times x plus 3 and x minus 3. Okay? So linear factors, hey, if we want to get really technical, which I would leave the x squared all put together, but if I'm doing linear factors, this is technically x times x plus 3 times x minus 3, x plus 5. We'll leave it like this. Okay, we're not going to get too technical. This is factored completely. We've broken it down into as many pieces as we can. Okay. Problem number 10. They're giving us one of the zeros. They're telling us that x equals 3 is a 0. And they're saying based on that, state all of the remaining zeros. And if it's necessary to put our answer in simplest radical form. Right? So what that means is if they're giving us one of the zeros, chances are we're not going to be able to factor the expression. And in this case, that is the case. If you tried to use the grouping method, okay, on this expression that we have here, you're actually not going to be able to factor it. It's not going to break down nicely. Okay, so what we're going to have to do is use some synthetic division, which I'll do off to the side here. I'm going to divide that x equals 3, 0 out of my f of x function and see what I'm left with. So let's make sure we're careful. Okay. One thing you want to always be careful with synthetic division is that you don't, if there's any skipped terms, that you put a 0 in there. So I have a cubed, a second power, a first power, and a constant term. So I'm not missing anything. So I just want to, you always want to double check that. So I'm going to say 1, 3, negative 30, and positive 36. Okay, so let's do our synthetic. Bring down the 1, multiply 3 times 1 is 3. 3 plus 3 is 6. Let's do another multiplication. 3 times 6 is 18. When I do my addition, I get a negative 12. 3 times negative 12, I'm glad, is negative 36, and I get no remainder. Remember, if they're saying something is a 0, you should always have a 0 remainder. So if you're not getting a 0 remainder in this kind of situation, you need to go back and look at your expression again and see if maybe you made a mistake with your synthetic, or maybe that case where you skip the zeros. The missing terms is happening there. Okay, so here's what I'm left with: x squared plus 6x minus 12. So let's see if we can factor this. In this case, can I find any numbers that multiply to negative 12 that add up to positive 6? Right. So I'm looking at this, and I'm looking through my list of like 4 times 3, 6 times 2. Right. It doesn't look like anything's working out, which means this is an expression that if I'm going to find the zeros, right, I'm going to set this equal to 0, and in order to solve this, okay, plus 6x, okay, in order to solve this, I'm going to have to use the quadratic formula, which is why they're mentioning the simplest radical form, because in the quadratic formula we do have to use that. So I'm going to say in this case, let's do negative 6 plus or minus the square root of, okay, well, b squared is 36, okay, minus 4 times 1 times negative 12, okay, so let's see what happens here, okay, this is all over 2. Okay, so my x equals, so let's put it in simplify the radical, right? Negative 6 plus or minus, well, 36, and this says plus 48, right? So we're doing 36 and 48. Okay, well, that looks like 82, right? Or 84, I'm sorry. All right, square root of 84. Okay, all over 2. And then to simplify this radical, the only thing that we have left to do, okay, is remove anything that's a common factor, or I'm sorry, a square rootable factor, right? One of our perfect squares. In this case, this has a 4 in common, so I'm going to turn this into negative 6 plus or minus 2 root 21 all over 2, and then one more little bit of simplification. Because I have 6 halves and 2 halves, I can simplify that one more time, and it's going to become negative 3 plus or minus the square root of 21. And so the remaining zeros, there's 2 more of them, okay, put a little x equals out here, okay, is negative 3 plus the square root of 21 and negative 3 minus the square root of 21, okay? So that's our synthetic division being used to help us get a simpler expression that we can then use to solve the problem, okay? So let's move this down because we're going to need some space here, okay? We need to do some long division, right? So in this case, I'm asking to do division, and this notation here is basically just asking you if you get a remainder, which is what r of x is referring to. If you get a remainder, put it in a form where you're putting the remainder over the divisor. That's how we set up remainders when we're doing division like this. So in this case, I need to set up a long division. So let's see how I can draw this. Okay, so I'm going to put the divisor, the bottom number on the outside, x squared minus 5. Okay, and we're going to divide that into this long expression. Okay, x to the 4th plus 4x cubed plus 5x squared minus 20x minus 50. Okay, and so if you remember what we said with this is, I'm going to take a look at this expression and I'm going to say, okay, x squared, I need to use this first term x squared to complete my first term here, x to the 4th. And I do that, it looks like I'm just missing an x squared. X squared times x squared will give me the x to the 4th. I'm going to put that way over here, right above the x squared in the original problem. And I'm going to multiply. X squared times, let's get rid of that, x squared times x squared is my x to the 4th. Okay, I'm going to subtract that away. X squared times negative 5 is negative 5x squared. Okay, so let's do a subtraction. Okay, the 4x cubed is just going to come down. There's technically a 0 in here that we didn't write out, but it's going to come down and just sit in this first space. Okay, be careful with this. This is 5 minus negative 5, which does not cancel. It's actually 10x squared. Okay, and then I'm going to bring down my next term, the negative 20x. Okay, so now we have to repeat this process until we run out of things to bring down, and then we have a remainder. Okay, so in this case, I have an x squared, and I need to complete a 4x cubed. Well, in order to do that, I'm going to use a 4 and one more x. Okay, so now let's do our multiplication. I get the 4x cubed. Okay, and then 4 times negative 5 is negative 20x. Okay. Now let's do our subtraction here. Okay, so remember this is a subtraction, so I'll get a cancel, just like we got with the x to the 4th. Bring down my 10x squared. Okay, and then this one, negative 20 minus negative 20 is actually going to turn into 0, so this one cancels, and I'm going to bring down my negative 50. So I'm actually going to attach it a little bit closer. Okay, so there I have that negative 50 there. Okay, last one, I need to turn x squared into 10x squared. Well, I'm going to do that with just a 10. Okay, multiply it out. 10 times x squared is 10x squared. Okay, 10 times negative 5 is negative 50, and in this case, we have a 0 remainder, nothing left. So if they're saying state the answer in this form, I'm going to say this x squared plus 4x plus 10. That is my answer. Okay, if I happen to have a remainder, so I want to give you a possible scenario. Let's say my remainder didn't come out to be 0. Let's say it came out to be 10. Okay, and so I have something left over. I'm done. I've brought down my last term. I did my last division, and I do have a remainder. What this statement here, q of x plus r of x over d of x is saying is that you would need to add to the end of this the remainder, which is 10, over the divisor, which is x squared minus 5. So again, that's not happening in this particular problem because we didn't have a remainder, but if there happens to be one, which that's going to happen a lot, not everything divides nicely, we're going to just kind of tack it on the end as a remainder over divisor type situation, so that we can include that in our final answer in the form that they're asking for, which is quotient plus remainder over divisor. Okay, so now that we're done long division, let's take a look at some slightly more straightforward problems. Okay, so problem number 12 is asking us to state the degree of these two polynomials and to describe the end behavior, and they're specifically asking us to use limit notation. After we've done both of those, the last thing is they're saying state the greatest number of possible terms, which I think is the easiest of them. Okay, so if you compare these side by side when they're asking us for degree, this is probably the hardest part of this, or the most confusing part of it, I think. In the right-hand problem for B, we're actually just going to look at the 7, and we're going to say that this is a degree 7 polynomial. So in this case, I just looked for the highest degree, the highest exponent, and that was my answer. So you would think you come over to the other one and you say, oh look, the highest exponent's 3, it's a degree 3. Okay, if you compare these two problems, the big difference between them is letter B is in what we call standard form, which means all of the factors were multiplied together and I have one big expression. That is the situation where you look for highest exponent. In this problem, I actually broke it up into all of its simplest factors. When that happens, we need to do something different. Okay, so for letter A, I'm actually going to count how many zeros I have. How many factors do I have? So I'm going to say in this case, I have 3 x's coming from negative 3x cubed, so that's 3. An x to the minus 5, that's 4. And then another 2x plus 2's, that's 5 and 6. This is actually a degree 6 polynomial, okay, because it's in factored form. I needed to count those factors, counting all of the duplicates, okay, and make sure that I represent it that way. So there are 2 different situations that we need to handle slightly differently. Okay, so let's start with letter A. Let's talk about the end behavior. So if we were describing this just in words, I'm seeing an even polynomial with a negative leading coefficient. We would call that down, down, right? So remember, all the even polynomials are traveling in the same direction, so they'll either both be up or both be down. But because we have a negative 3 at the beginning of this, that's going to send it down instead of up. Okay. So now that we have it down, down, we need to write it in limit notation. So what this means is on the left-hand side, so let's write about the left-hand side, we're going to say as x approaches negative infinity. This just means the left-hand side. Okay. Now I need to describe what's happening on the left-hand side. It's going down. So I'm going to say f of x, the function is going down, the function is approaching negative infinity. Okay. And I'm going to do the same thing on the right-hand side. I'm going to say as x approaches infinity, which means the right-hand side of the graph. Okay, I'm describing the function as also going towards negative infinity. It's going down. Okay, so if I do that with this one, it's the same basic idea. Odd polynomial, I can describe this one as down, up. Okay, and again, it's down, up because it's got a positive 12 in the front, and they start down, up. Nothing flipped it over, so I'm going to leave it just how it is. Okay, so if I'm describing this using limit notation, I'm going to say as x approaches negative infinity, which again just means let's describe the left-hand part. Okay, it's still going down. So just like this one, it's going to be the exact same thing. I'm going to say f of x approaches negative infinity. So that's describing the left-hand side of the graph is heading down. Okay, on the right-hand side, it's going up. So I'm going to say as x approaches positive infinity to tell people about the right. I'm going to say that f of x is going up, so it's approaching the positive side of the graph. So I'm going to write that as positive infinity. Okay. Last thing that they ask for, we don't want to forget about anything. It says the greatest number of turns. We're going to say it's always degree minus 1. So if this is a degree 6 polynomial, we're saying at most 5 turns. Okay. And I can do the same thing for letter B, 7th degree. So I'm going to say at most. Okay. At most. Getting a little bit of jumpiness here. At most 6 turns. There we go. Okay. So 3 different pieces to this: degree, end behavior using limit notation, and the number of turns. Okay. All right. Problem number 13. It says there is a function that has zeros at x equals 2, x equals 0 with a multiplicity, and x equals negative 7. They're showing a negative leading coefficient, and they're saying, give me some possible sketch that could represent this. Okay, so this is pretty straightforward. Okay, we can say x equals 2. Let's put that on the graph. That's one of my, remember, zeros are really x-intercepts when we're on the graph. Okay, x equals 0. Okay, and x equals negative 7. That's way over here. Okay. It has a negative leading coefficient. So let's think about the degree of this. Okay, so we have to decide about the end behavior before we do any graphing. Okay, I'm going to say this has 1, 2, 3, 4 zeros. It's a degree 4 polynomial. Okay, and because it's degree 4, it needs to be traveling in the same direction. Negative is going to mean down on both sides. So it's down on the right and it's down on the left. Right, so we'll describe this as down, down. Right, and we don't need to write this. This is just for our reference to remember. Okay, so down, down. Okay, and it has a multiplicity of 2 at x equals 0. So that means that when it gets to x equals 0, we need to make it look like a parabola, or the bottom of a parabola. Right, that little U shape. So let's graph this. Right, so we're going to say pretty straight through at x equals 2. It's going to come down. Okay, we don't know how high it goes, but we know it goes down. It bounces, and then it goes straight through. Okay, let's pretend like that's straight through. Let me fix that. Okay, we want that to look pretty straight. Okay, so we're going to go through and we're just going to say straight through. Okay, and it'll look something like this. Again, this is a rough sketch. It may go way higher before it comes back down and bounces, and it might go way high again. We don't know that. We just know about multiplicity. Okay, we know that it's heading down, down, and we know what the zeros are in this case. Okay, so we have a couple more problems. Okay, problem number 14. Write a polynomial that could produce the zeros in problem number 13. So again, let's take a look at what they tell us in problem number 13. Has a negative leading coefficient. It has 3 different zeros, and one of them has a multiplicity. So let's see if we can describe this and write something that could represent this graph. Okay, so if I have a 0 at x equals 2, okay, and I'm turning this back into a factor. Remember, x equals 2 would turn back into a factor by setting it back equal to 0. That's why we call them zeros. Right? So I'm going to say in this case, x minus 2 equals 0. Okay? X equals 0 I don't need to do anything with. I'm going to say, well, that's just x. X is a factor. Right? But I need to remember that there were 2 of them, so this actually is going to produce x squared. Right? X squared equals 0 still works, but I'm actually going to count 2 of them now. Right? There's 2 different x's there. Right? And I can do the same thing with my third 0, which I believe was -7. Right? I have this -7. So when I say x equals -7, okay, I'm going to say, well, that would come from an x plus 7. Right? So I have my 3 zeros, x squared, x minus 2, x plus 7. So let's write those down. So I'm going to say x, if I multiply together x squared times x minus 2 times x plus 7, that would be an expression that could give me this polynomial. We started with the zeros to get these factors, which means these factors will give us those zeros. Okay. We have one more thing we have to take into account, though, and that is that this has a negative leading coefficient, so I have to make sure that I put that negative leading coefficient, and you can put whatever number you want. So we could say in this case, in factored form, okay, this would be an answer. So if they ask us to write it in factored form, we're done. If they ask us to write it in standard form, we're not done. We have to multiply this out. So I'm going to multiply together these two while they look nice and simple. I'm going to say in this case x squared plus 5x minus 14. Okay? And then I can just distribute this negative x squared in. And in standard form, I would say negative x to the fourth, okay, minus 5x cubed plus 14x squared. Okay, so if they're asking us for a polynomial that could produce the zeros and probably looks something like the sketch that we just drew, this expression, negative x to the fourth minus 5x cubed plus 14x squared, is an expression that could have done that. Okay, last problem, problem number 15. Okay, they are asking us to find the b value if I divide x minus 9 into this expression. We don't know the whole expression, we're missing the middle term. Right, and I get a 14 as the remainder. So this is a way, we can do this 2 different ways, and I'll show you both of them. One of them is we could do synthetic division. So let's do that. If I was dividing x minus 9 into this expression, that's what they're asking us to do. Let's do it. Okay, I could just do, okay, put my 9 on the outside. Remember, when it's a factor, we have to actually set it equal to 0 and solve. So I solved it and got a 9. Okay, and I'm going to say 3, b, and 10 are my 3 coefficients. So we're going to go through and do synthetic division the good old-fashioned way. Okay, we're going to bring down the 3. 9 times 3 is 27. Here's where the algebra comes in. This says b plus 27. The only way I can write b plus 27 is to just write exactly what I said, b plus 27. Okay, now I need to do another multiplying. Okay, 9 times b is 9b. And 9 times 27 would be 243. Right? 9 times 7, 63. 9 times 2 is 80. Yep, 243. Okay. Oh, sorry. I put that in the wrong spot. 243. I was so worried about getting my math right that I put it in the wrong spot. Okay. So when I do this multiplication, 9 times b, I get 9b. 9 times 27 is 243. So I get this new expression, 9b plus 243. Okay. And then I need to just do this. 10 plus this expression would be 9b plus 253. Okay. This is the remainder. Remember, if we get the last term, that last row, that last column, this expression, 9b plus 253, that should be equal to 14. So we can figure out now what b is. So let's do a little bit of algebra. I'm going to do 14 minus 253. Okay, 14 minus 253 is negative 239. So I can say in this case, 9b equals negative 239. Okay, and then I can divide both sides by 9. And in this case, I get something that's not really all that nice, and that's okay. That's going to happen sometimes. In this case, b is equal to negative 26, and we'll just round 0.6. So it's 0.5 repeating, right? But we'll say about negative 26.6. Okay, that's one way to do it. The other way to do this would have been to use the remainder theorem, and what the remainder theorem says is if I plug, okay, the answer to this problem into this expression, I should get my answer, right? So in this case, I'm going to do the same thing. I'm going to say 3 times 9 squared plus b times 9 plus 10. And I'm going to simplify this. Well, this says 81 times 3. 81 times 3 plus 10, guess what, is 253. Okay? 9 times b is 9b. Okay? And if you notice, okay, that's the remainder. And that's the exact same thing that we had here when we did it the synthetic division way. So it's two different ways of getting to the same place. Here I actually did the division and got an expression that represented the remainder. Here the remainder theorem says if you plug in the 0 that x minus 9 will produce, which is 9, that expression will be the remainder. So in this case, 9b plus 253 equals 14. And I'm going to get the same answer. It's the same expression. Okay, so that's our last problem on the remainder theorem, right? So all of these are available to you. The paper copy of the key is also available. So this should hopefully help you to prepare for the unit test. Everything that you saw will be on unit test number 2.